Hello, students. Welcome to our calculus lesson for today. I'm Barack Obama, and today I will explain the concept of the gradient.
Hey, Barack, we heard you were teaching calculus today. Mind if we join in?
Yeah, I really need a break from my Minecraft all-nighter.
Of course, guys. So what is the gradient? In calculus, the gradient is a vector that points in the direction of the greatest initial increase of a function. It describes the surface's rate of change.
Barack, this sounds a lot like a slope of a line.
Yeah, I learned about this stuff back in the 7th grade.
Think of it as the multidimensional equivalent to the slope of a line. Past 2D, the concept of slope doesn't really make any sense. There are an infinite number of different directions you can go in to find the rise over run. So the gradient only focuses on the biggest jump of the z value, or height. Take this hill, for example. At this point right here, the greatest initial increase will be in this direction. That is the gradient vector of that point. Every single point of the function will have its own gradient vector.
That's some crazy stuff, man, but how do we find the gradient?
Think back to your day 1 calculus class. The derivative of a function tells you the slope at a certain point. To find the slope in every direction of a 3D function, we find the partial derivatives of the function with respect to each of its variables. The result is a vector that tells us how quickly the function changes and in what direction is the largest increase. Take the function f of x, and y is equal to a negative x squared plus y squared plus 10. The function has two inputs, x and y, and will output a z value. To find the gradient, let's take the partial derivative of all the variables and add them together. So the partial derivative of x is negative 2x, and the partial derivative with respect to y is negative 2y. So the gradient vector is just negative 2x, negative 2y.
Oh, I'm getting it now. We got a variable vector that we can input different values into, so we can find the direction of the greatest initial increase at that point.
Yes, Joe, now you're getting it. For example, let's say we want to find out which direction the first step up on the fastest way up this hill will be. But we start at the point negative 5, negative 3. We just have to plug in those points to our gradient vector. And we see that the gradient at negative 5, negative 3 is 15.6. Now we know that we have to go initially the direction of 15.6 for the quickest path up this hill.
So the gradient always points to the max of a function?
No, this is an extremely common misconception. Remember, the gradient points in the direction of greatest initial increase, not the greatest value of the function. For example, if we had a function of a hill with two peaks, except one was slightly taller than the other, and you are closer to the smaller peak, the gradient would tell you to start climbing the smaller peak. This is because the gradient cannot ever tell you to go downhill.
So if there's only one peak, the gradient vector will always point to that max?
That's also wrong, Joe. Let's say the steepness of the hill is different on all sides. If Donald was at the foot of this hill, over here, the gradient vector would tell you to walk in this direction. While it does mean you ascend, at first, notice how if you walk in this straight line, you won't hit the absolute top of the hill. If you want to get to the top of the hill, Trump will have to recalculate the gradient vector's direction for every step he takes. This is called the gradient path.
Obama, is that really all there is to the gradient vector? So now we can find the fastest way up a hill? Big deal. I don't get what the fuss is about.
The gradient vector is so important because of all of its outside applications. Remember how back in Calculus 1, you use the first derivative to find a function's max and min.
Yeah, I remember getting a 32% on that test.
Maybe it's because you fell asleep during the exam, Sleepy Joe.
Well, you can use the same concept for 3D applications with the gradient vector. When the gradient is equal to 0, 0, there are three possibilities of where you are. One of the function's max, mins, or saddle points. These are called critical points.
Oh, I remember saddle points. They're the region of surfaces that look like a saddle.
Yeah, that's why they're called saddle points, doofus.
Anyways, let's go back to our hill defined by f of x, and y is equal to negative x squared plus y squared plus 10. We calculated before that the gradient of this function is negative 2x, negative 2y. So what does that tell us about the function's critical points when the gradient is 0, 0?
The point 0, 0 could be a max min or a saddle point.
Good job, Donald. And since we can see that this function has no minimum or saddle points, the point 0, 0 has to be a maximum. Now, who can tell me the altitude or z value of this max?
Would you plug in 0 back into the original function? So f of x and y at 0, 0 equals negative 0 squared plus 0 squared plus 10, which equals 10. So the 3D coordinate of the max is 0, 0, 10.
That's correct, Joe. See how we got all of that with just the gradient? And that's not all. In Calculus 1, you use the first derivative to create a linearization of a tangent line to the curve. With gradient vectors, you can create tangent planes in 3D class. What do we need to create an equation of a plane?
We just need two vectors on the plane.
Exactly right. So if you find the gradient vector at any point on the surface, all you need to do is to get the normal vector of the gradient to create both the plane vectors. The possibilities are endless.
This is some great stuff, Barack.
Yeah, I'm starting to feel smarter already. If only I could gradient this to fix the economy.
Good joke, Biden. Well, guys, that's all for today. Tune in for our next Calculus 3 lesson.